In a previous chapter, we talked about equilibrium constants. And the equilibrium constants helped us predict whether reactants or products were favored. Well, like all equilibria, we can write an expression for the equilibrium constant for acid-base reactions that take place when a weak acid is dissolved in water. The acid dissociation constant is the result of the equilibrium constant for an acid. So the equilibrium constant for an acid, remember we used K for the equilibrium constant, but it has a little a. And we call this the acid dissociation constant. This acid dissociation constant shows us the ratio between the concentration of the products and the concentration of the reactants. As we understand this, we can relate the Ka, or the acid dissociation constant, to the strength of the acid. And it's kind of a helpful number to help us know how strong our acid is. The stronger the acid, the larger the value of Ka. Stronger acid, larger Ka value. Now there's several things that we need to just remind ourselves of. So here's two examples, HCN and HSO4 negative, along with their acid dissociation constants. So recall that in negative exponents, which these have, the larger the negative exponent, the smaller the number. So a negative 10 is a smaller number than a negative 2. So since the HSO4 negative has a larger Ka value, then we would know that it is the stronger acid. Now what does it mean to be a stronger acid? Here's some of the properties of stronger acids. Stronger acids dissociate to a greater extent, which means they form more ions. I just mentioned that they have larger Kas. And an interesting relationship which we saw in a previous video is that the stronger the acid, the weaker their conjugate bases are. Remember that Ka values are associated only with weak acids. Strong acids, remember there's like a short list like hydrochloric acid, hydrobromic acid, sulfuric acid. Strong acids dissociate completely and don't have Ka values. So our values here are just going to be for weak acids. So again, to just kind of contemplate on what it's telling us, here the first thing is, the stronger the acid has a weaker conjugate base. The stronger the acid produces more products. Another way to say that is that the equilibrium will be further to the right. So if we think about a chemical reaction where the reactants are on the left and the products are on the right, a stronger acid produces more products, so it would be further to the right. So then if we're looking back up at the two acids that started out the original example, we could see that this acid is the stronger acid, which means that it has a weaker conjugate base, so its base is weaker than the weaker acid. So HSO4 negative has a weaker conjugate base. The other thing that we could point out is that HSO4 has an equilibrium that's farther to the right, which means that it is going to produce more products. Again, because those are characteristics of being a stronger acid. So let's go to the next page. I have two problems where you can try to put these ideas together. If you'd like to pause now and try to answer the questions before I answer it. So the first question says, which compound is the stronger acid? Phosphoric acid, which is H3PO4, or acetic acid, which is CH3COOH. To evaluate this, given the Kas, I will take a look at them. And I know that the stronger acid has a larger Ka value. Kas are important in helping us distinguish between the strength of weak acids. So this one has a -5, and this Ka has a -3. The smaller the negative exponent, the bigger the number. So this is a larger Ka. And so the larger the Ka, the stronger the acid. So the stronger of these two acids would be the H3PO4, which is phosphoric acid. The second question says, draw the conjugate bases of each and predict which base is stronger. So what we recall, so here's my two acids as given in letter A. And what I know, acids donate their hydrogen. This one will donate the hydrogen in the front. So if I take away one H plus, I get H2PO4. When I'm taking away H, so I'm thinking I'm taking away H plus. When you take away a plus, you have to leave a negative behind. Acetic acid, here's my COO, so this is the H that's going to come off. So if I take an H plus off, I get CH3COO. The H is going to come off, and it leaves a negative behind. So these two formulas right here are my conjugate bases. What I know is that the weaker acid will have the stronger conjugate base. And so predicting from up letter A that H3PO4 is the stronger acid, then I would know that this, the acetic acid, has a stronger conjugate base. So let's try a second problem that uses some of the same ideas. So again, I would recommend that you pause and see how far you can get with the answers, and then we can take a look at it together. So this says consider the weak acids, and it gives me HCN and H2CO3, and they both have their acid dissociation constants, or Ka. So the first question simply says, which one has the larger Ka? Looking at the exponents, I know that a -7 is larger than a -10. So H2CO3 has the larger Ka. So which acid is stronger? I know that H2CO3 will be the stronger acid because the larger Ka is associated with a stronger acid. Let me mention here that Ka values are not something we memorize. They'll either be given as in these problems, or you'll be given a table that contains these values. Letter C says, which acid has the stronger conjugate base? So I know it's an inverse relationship, so the weaker acid would have the stronger conjugate base. So the weaker acid has the smaller Ka, so HCN, which is the weaker acid, would have the stronger the stronger conjugate base. Likewise, I would predict that H2CO3 or carbonic acid would have the weaker conjugate base. It's the opposite. And then letter D says, when each acid is dissolved in water, for which does the equilibrium lie further to the right? So further to the right, and I'm going to bring it up here. This means it makes more products. And something that makes more products is going to be the stronger acid. And so the stronger acid has a higher Ka value, so the stronger acid is H2CO3. So this is the answer to letter D.